Okay, so the homework due today was 3.3, numbers 1 and 4. There's no questions, so we're continuing from last class. So at the end of last class, we had another example from the material we just covered on vectors. And so this is the example. Find a vector equation and parametric equations of the line in 3 space that passes through a point P naught 1, 2, negative 3, and is parallel to the vector V, which is 4, negative 5, 1. So we want a vector equation and parametric equations of the line in 3 space that passes through that point is parallel to that vector. So the equation that I wrote for you is that x is equal to x naught is equal to x naught plus t plus t1 v1. So yeah, that's good. Okay, so plus tv, since it's a line, so there's only going to be one, so you don't need an index if there's only one. So x equals x naught plus tv, right? So then that means x naught is the point p naught, which is 1, 2, negative 3, plus t times the vector v, which is given to you 4, negative 5, 1. So this is a vector equation. So the above is a vector equation of this line, okay, the problem. So that is a vector equation. Okay, now to find parametric equations of the same line, then you just equate each of the components on both sides of the equal sign to get, well, what you have is that the x components are the same. So you have x as a point. X as a point is equal to x, y, z, which is equal to this. So again, I mentioned this last class, mathematicians like to reuse notation. So mathematicians reuse this notation. X is representing a vector whose first component is x. Here, x is the first component of this vector, and here x is being reused to be the name of the vector, okay? It's actually a very simple and easier to read way to explain something, right? It's easier to read if you reuse the same symbol to mean 2 different things, rather than constantly using new symbols when the meaning of something only changes slightly. The meaning of this has not changed much. We're still talking about the same vector. Its first component is x. And so we just want to use x to represent it twice. Okay, so these are essentially 2 different x's. This x is not the same as that x, okay? So while in elementary school and early in math, you saw different symbols, they would represent different things. They could be equal, but they represent different things. In more advanced mathematics, the same symbol keeps being used over and over again, and each time it could mean something slightly different. But there's usually similarities to the things that are being used with the same letter, okay? So anyway, so x, y, z is equal to the sum of those 2. So you just set each of the components equal to the first component is x on the left side, and the right side is 1 plus 4t. The second component on the left side is y, and the second component on the right side is 2 minus 5t. The third component on the left side is z, and that's equal to the third component on the right side, which is negative 3 plus 1t, which is t. Okay, so these 3 are the parametric equations that describe the same line. So the 3 equations above using t are the parametric equations describing the same line. Okay. Okay, so these are the parametric equations. This one equation is a vector equation. They each have the exact same amount of information. This one vector equation has the exact same amount as those 3 parametric equations. And nothing is added or lost from either of them. Okay, So so C, I could say find 2 points on the line in A different from the initial point P naught given in the problem. So to do that, you can just think of different values of T. Okay, when T is 0, then a point on the line is 1, 2, -3, which was given. Just choose 2 different values that are different than T equals 0. So use 2 different values of T other than 0 to find 2 points on the line that are different from each other and different from P naught. Okay, so when T is equal to 1, little t is equal to 1, that implies that a point on the line represented by T equals 1 is, there we go, there's a simple. Okay, then the corresponding point is when X is equal to this, the point on the line is this, where T is 1. So there's a 1 there. And so the point you get is the first component is 1 plus 4, which is 5. The second component is 2 minus 5, which is -3. And the third component is -3 plus 1, which is -2. So you get 5, -3, -2. When T is equal to, let's say, 2, that implies that the point X is equal to this expression again, except when T is 2. There's a 2 now here. And so now what is that when T is 2? The first component is 1 plus 2 times 4, which is 1 plus 8, which is 9. The second component is 2 plus 2 times -5, which is 2 minus 10, which is -8. And the third component is -3 plus 2 times 1, which is -3 plus 2, which is -1. The other point is 9, -8, -1. So these are 2 points that are on the line that are different from the initial point, P naught 1, 2, -3. Okay, so with that example is done. Here's another example. This is example 2. Find vector and parametric equations of the plane. And so the plane is represented by x minus y plus 2z is equal to 5. And so here's the solution. Find vector and parametric equations of that plane. Okay, so solving for x, we get that x is equal to y minus 2z plus 5. Okay, so what we did now is we express x in terms of y and z. So set y equal to t and z equal to s. Then x is equal to t minus 2s plus 5. Because x is equal to y minus 2z plus 5, and we set y equal to the parameter t and z equal to its own parameter s. And so we just plug in t for y and s for z. We have an expression of x in terms of the 2 parameters t and s. Okay, so what that means is that x is equal to t minus 2s plus 2 minus 2s plus 5, comma, y equal to t, comma, z equal to s are parametric equations for the plane. Okay, well, so how do I know that I can set 2 of them equal to parameters, right? So what I want to do is I essentially have one equation, right? I only have one equation with 3 unknowns. And so that means that if I wanted expressions for each of 3 variables, the only way to, in a sense, eliminate a variable is I could say one of those 3 variables is equal to an expression of the other 2, right? So obviously you could choose any of these 3 variables and set equal to an expression using only the other 2. And so that's really all I can do. And so for whatever variable on the left side, in this case x, I could set all the other variables on the right side that are different from it to each its own parameter and then I could in a sense parameterize all three variables using two parameters, right? I can't do it with only one parameter. I need two parameters because the only way to simplify this is to say one of the variables equals an expression of the other two. Okay, so I need two parameters to express x as an expression of parameters. I can't do it with only one. And so we now have a parametric equations of this plane by those three equations. Okay, so in this example, we got parametric equations first, while in the other example, we got the vector equation first. Sometimes it's easier to see the vector equation. Sometimes it's easier to see the parametric one. In this case, the first thing to find are the parametric equations. So in this problem, we now have the parametric equations, and we can now find the vector equation of the plane. Okay, so we now work to obtain the vector equation of the plane. Okay, and so if you have a point x on the plane whose coordinates are x comma y comma z, it's equal to well, the x coordinate is given right by this expression. This is an expression for this first coordinate of a point in terms of t and s. Y is equal to t, which means that t is an expression describing the second coordinate of a point in the plane. Z equals s, so that means that s is an expression for the third coordinate of a point on the plane. So we can now express x is equal to x comma y comma z, where it's equal to t minus s plus 5 comma t comma s. Okay, so we've now expressed it as that. Okay, so I want to use vertical representations of the same thing. So let me point out that I'm going to switch to vertical because I think it's easier to see. So here, you can think of x as equal to, right, x, y, and z. And so this is equal to the first coordinate t minus 2s plus 5, second coordinate t, third coordinate s. So remember, a finite n tuple is just having commas here. It's a horizontal list, essentially, right? So an n tuple is a horizontal list. Like an ordered pair is a list of two things horizontally, or a three tuple is an ordered list of three things. Having a list horizontal or vertical changes nothing. It's the exact same thing. The list isn't any different if you write the list horizontally or vertically. So here, I'm just making the list vertical instead of horizontal. So it's the same thing. So x is equal to x, y, z vertically. It's equal to t minus 2s plus 5 ts vertically. And now I wrote it vertically because I want to express this as a linear combination of vectors where coefficients are t and s. So let me explain. So I want to express this as t times something plus s times something plus another vector. Okay, and there are three components, right? There are three components. So these are actually having three components here. The first component is 1t. There's 1t in the second component, and there's 0 t's in the third component. For s, there are negative 2 s's in the first component. There are 0 s's in the second component, and there is 1 s third component. Last thing is the constant. There's a constant 5 in the first component. There is no constant in the second component, and there is no constant in the third one. I've now expressed x as t times a vector plus s times a vector plus another vector. Okay, and so now this is a vector equation of plane. Okay, so x is equal to this expression. Is a vector equation of the plane. Okay, because we're not looking at coordinate, even though I wrote down the components of these vectors, I'm not looking at these vectors component by one component. I'm not separating, I'm not looking at component by component. I'm looking at the whole thing at once. Okay, and this expression is using vectors. This is a vector, this is a vector, this is a vector, and that as a linear combination of vectors is a vector. So all the things we're just dealing with vectors that we're adding and multiplying. So it's a vector equation. It's an equation consisting of vectors. Okay. Okay, so then that is a vector equation of the same plane. Okay, so these examples are kind of fun once you get it. They're very visual. I like visual problems. So find vector and parametric equations of the line through the origin of four space, the space of all four tuples, that is parallel to the vector v, which is equal to 5, comma, -3, comma, 6, comma 1. Okay, so find vector and parametric equation of the line through the origin of four spaces parallel to that vector. Okay, so let's use our equation from earlier. So our equation is saying that that you can think of x being a point or a point in the plane represents a vector or as a point is equal to an initial point plus to want a line. So it's just going to be t times x naught plus tv. Okay, it's plus tv, only using only one t because a line is one dimension. Okay, so this is equal to it's through the origin, which means x naught is 0, and plus t times a vector v, where v is given as 5, comma, -3, 5, comma, -3, comma, 6, comma, 1. Okay, and so this is equal to t times that vector, right? Okay, 0 is used to denote the four tuples 0. So 0 here is 0, comma, 0, comma, 0, comma, 0. Okay, so I don't want two parentheses there. Okay, good. So I just got rid of the 0. So now, okay, so when you multiply that by t, you get first component is 5t, second component is -3t, the third component is 6t, and the fourth component is t. 1 times t is t. 1t is t. Okay. So now we have that x is equal to that. I am recording. Okay, so now, okay, so forward. Looking back before. Okay, so x is equal to that. So we now have our parametric equations. X is equal to 5t, where x is the first component. Y is equal to -3t, where y is the second component. C is equal to 6t, where z is the third component. And w is equal to t, where w is the fourth component. Okay, so here, the x here can be represented component-wise by x, comma, y, comma, z, comma, w. Usually you start with x, so you have x and then x comma y, x comma z, x comma y comma z. And even though w is before x, there is no letter after z, and so you don't start with w usually. You just then end with w. Okay. If there's four components, x comma y comma z comma w, so then w is t, the last one. Okay, so the above four equations are the parametric equations of the line in the problem. Okay, so those are the parametric equations, right? And so we already have the vector equation from here. The equation x is equal to t times this vector. That's the vector equation. Okay, so the above equation is the vector equation of the line. So a vector equation is one equation. Parametric equations are a set of equations. Okay, so that's part A. We found the vector and parametric equations for that line. So for part B, we have another question. So for part B, find vector and parametric equations of the plane in four space that passes through the point x naught, which is equal to 2, -1, comma 0, comma 3. And it's parallel to both v1, which is equal to 1, comma 5, comma 2, comma negative 4, and v2, which is equal to 0, comma 7, comma negative 8, comma 6. Okay. Find vector and parametric equations of the plane in force space that passes through the point x naught equals 2, negative 1, 0, 3, and has parallel to both v1 and v2 there. Okay, so if you represent an arbitrary point x in this plane as any point on this plane as x, x is going to equal to x naught, an initial point, plus a first coefficient t1 times the vector v1, plus the second coefficient t2 times the second vector v2. So this is an expression to describe all points on a plane. Okay. So again, I did this last class. I'll write it again, help you. So then here's let's say the x-axis, the y-axis, and this is the z-axis. So if you have an x naught, right, this is your x naught vector or point in the space x naught, which is the tip of that vector starting at the origin. Then if you have two parallel vectors, you draw them from that point. So here's v1 and here's v2. And then your plane, it just goes through that point at the tip of the vector x naught, and then is parallel to those vectors, meaning that it'll look something like this. Okay, it contains this point x naught, and it's a plane parallel to those two vectors. And so it'll continue in all four directions infinitely as a plane, but it has to go through that point x naught, and it has to be parallel to those two vectors. So that's a picture of what that plane would look like in 3 space. In 4 space, you just have another dimension. So all these 3 vectors have a 4th dimension, and this plane is still a plane. It's still 2-dimensional. It just lives in 4 dimensions. Okay. If you had a plane in 2 space, it would just be all 2 space. If you had a plane in 3 space, the world we live in, it's a plane. So it's flat, it goes infinitely in all directions, but you could go other places because it's only 2-dimensional, and 3 space is 3-dimensional. In 4 dimensions, you still just have a plane, and you just have, instead of having one other direction you could go in, you have 2 other directions, which would be hard to visualize. But in a sense, the picture is just very similar, except you have another axis. Let's call it just W. So I'm just gonna have a 4th coordinate axis called W here. And so you have 4 coordinate axes, somehow hard to visualize, but you still have a plane with an initial point x naught and 2 non-collinear vectors v1 and v2 that the plane passes through, parallel to. Okay, so that's the algebraic representation of that plane in 4 space. So this is equal to the point x naught given in the problem, which is 2, negative 1, 0, 3. Okay. 2, negative 1, 0, 3, plus t1, the first coefficient of vector v1, which is given as 1, 5, 2, negative 4, plus t2 times the second vector, which is 0, 7, negative 8, 6. So this is an expression so if you know this expression, right, if you remember it, you could plug in, right? But it's hard to memorize something if you don't understand it. So it's important. It really helps to understand it, even if you're just even if you're using the formula. Understanding the formula helps you remember it. So, okay, so now you have a vector representation of that plane. Okay, so you have x is equal to this. So x equals that. So the above equation is a vector equation of the plane. Okay, so that's a vector equation of the plane. And so we also want parametric equations. So once we have the vector equation there, you can just think, well, x is equal to the point whose coordinates are x, y, z, w. And it's equal, right, to this thing we have for the vector equation of the plane. So now you just set the components equal to each other on both sides. So x is the first coordinate. It's equal to 2 plus t1 plus 0 t2, which is just plus 0. Y is the second component. On the left side is y, and on the right side it's -1 plus 5t1 plus 7t2. The third component on the left side is z, and the third component on the right side is 0 plus 2t1 minus 8t2. And the fourth component on the left side is w. The fourth component on the left side is w. And on the right side, the fourth component is 3 minus 4t1 plus 6t2. So now we have the first, second, third, and fourth components, equations describing each of the four individually, as opposed to the vector equation that describes all four at the same time. So we're not adding or removing information. It's the same information, just done with more equations. Okay, so the above four equations are the parametric equations that describe the line. Or I shouldn't say the. Okay, it's not the only way. So are parametric equations that describe the line. Okay, so we now have answered part B. That was the goal of part B, to do both those things. We did. Okay. Question? Okay, so if x naught and x1 are distinct points in n space. Remember, I'm writing n space every time. By n space, I mean Rn, right? Okay, so if x0 and x1 are distinct points in n space Rn, then the line determined by these points can be expressed as x is equal to x0 plus t times x1 minus x0. And I'm going to denote this as equation 1 in this section, or equivalently, an equivalent way to write that equation is x is equal to 1 minus t times x0 plus t times x1. Equivalent just means that it has the same solutions, or its graph is the same. Okay, so this is not 1, this is 9. That's equation 9 in this section. This is equation 10 in this section of the book. Okay, the solution set of this equation is the same as the solution of that one. When two equations have the same solution set, they are equivalent. When they have a different solution set, they are not equivalent. Since all we care about the solutions, equivalent equations, there's nothing wrong with looking at an equivalent equation. That doesn't matter, right? We don't have to deal with a particular equation. Okay, so these are called the 2-point vector equations of a line in n space. I'm going to write Rn there. Rn. Okay. Okay, so the idea of that, the meaning of that is you want to express, it's an expression for the only line that can go to two distinct points. So if you have a point here, which we call x0, and we have a point here, which we call x1, and this is a point, these are points living in n space. And so it's not a certain number of axes. So here I'm drawing 3 axes, but it could be 2. It could even be 1, but that would be wouldn't be interesting. It could be 10 coordinate axes and so forth. So we're living in Rn. So you can imagine that there's possibly more than 3 coordinate axes or less. So we want the only line that goes through these 2 distinct points. So I'm going to draw the line first. is this pink line. It's going through those 2 points. And making the points bigger. Okay, so it goes through the points x naught, that's x naught, and that's x1. And so one way to express this line is to say, okay, well, I could start at the origin. I could go along the vector x naught, right? The vector x naught would just be the vector that starts at the origin at the tail, and the tip is at x naught. So then once I get to x naught, all I need to do is go along a vector x naught, x1 minus x naught. So if I were to say, okay, I want to go along this line. So I'm going to go along this green vector, where the green vector is x1 minus x naught. The vector x naught, x1, points in n space can be seen as points or as vectors, where the initial point can be thought of as the origin, and the tip could be the end of it could be thought of at the point that you're talking about. Okay, so first we think of x naught, x1 as points, distinct points in n space. Now I want to think of x naught and x1 as vectors, and so the vector x1 minus x naught as a difference of vectors is a vector. It's a vector that goes from x naught at its tail to x1 at its tip. So if you start the vector x naught, which goes from the origin to the point x naught, then the vector x naught minus x1 would bring you to x1. Okay, so it's a way of getting from the origin to x1. Now, if you just take any multiple of that vector x1 minus x naught, you can go from x naught to any point on the line. So this vector x1, for multiples of it, could bring you to other points on the line. Okay, so for instance, if I were to talk about, if I were to look at 2 times x1 minus x naught, then it could possibly bring me there, right? So then this point would be like, this would be like the vector 2 times x1 minus x naught. And if I did the vector x naught plus 2 times x1 minus x naught, I would end up at this red point here. I would say, okay, x naught brings me here, and then 2 times x1 minus x naught would bring me there. I started here, and I ended up at that point on the line. I could do the same for every point on the line. I can get to every point on that line, on this pink line, by doing x naught plus a constant multiple of x1 minus x naught. So I can express this line as x is equal to x naught plus t, where t is just a constant multiple, times x1 minus x naught, where t ranges over all real numbers. So for each real number, you would have a different point. But if you take each of the real numbers one at a time, together its aggregate would be the entire line. Okay? And so this is the same as x equals x naught plus tv, but the v here is x1 minus x naught. Okay. Okay, so these are called 2-point vector equations of a line. This equation is equivalent to that one, has the same solutions. And so since it has the same solutions, its solution set is described by the same line, describes the same line. Okay. Example. Find vector and parametric equations for the line in 2 space that passes through point P, which is at 0, 7, and the point Q, which is at the point 5, 0. Okay, so solution is that PQ, so the vector PQ, the vector starting at point P and ending at Q, I'm just going to add the symbol, the arrow symbol at the top. Okay, so the vector PQ, starting at P, ending at Q, you just subtract corresponding points. So you have 5 minus 0, comma 0 minus 7. You have to keep the order the same, which is sometimes confusing. The first coordinate of Q minus the first coordinate of P is 5 minus 0. The second coordinate of Q minus the second coordinate of P is 0 minus 7. The order which is given by this notation, the going from point P to Q means you take you take the components of Q and you subtract each of them correspondingly by the points in P. So that's why you have 5 minus 0, 0 minus 7, and not 0 minus 5, 7 minus 0. Okay, so this is equal to 5, negative 7. That's the vector PQ, starting at point P, going to Q. Okay, so this tells you that X, which is the representation of this line passing through point P and then going through Q, is equal to X naught plus TV, where X naught is the point P, which is 0, 7, plus T times the vector PQ, whose components are 5, negative 7. Okay, and so then if you add those two, so then that's the vector equation of the line vector and parametric equation. So X is equal to 0, 7 plus T times 5, negative 7 is a vector equation of the line. Okay, and then parametric equations are X. So X is equal to 0 plus 5t, or X equals 5t. Y is equal to 7 minus 7t. Those two equations are the parametric equations of the line. Okay, so the parametric equations is a set of equations. So these two equations together as a collection, are the parametric equations of the line. Okay, so we found the vector and parametric equations for that line. Okay, so now a definition. If X naught and X1 are vectors in n space, then the equation X is equal to X naught plus T times X1 minus X naught. This is for 0 less than or equal to T less than or equal to 1, defines the line segment from the point X naught to the point X1. So instead of the line going through the entire line, it's just the segment from X naught to X1. When convenient, so in the book, this is equation 13. So 13 here is to just number it. So when convenient, equation 13 can be written as X is equal to 1 minus T times X naught plus T times X1, where the T values range from 0 to 1 inclusive. So 0 less than or equal to T less than or equal to 1. And this is equation 14 in the book in this section. Okay, it's just the same result before where we were describing a line, except we cut off the T values. Instead of T being all real numbers, it's T from 0 to 1 inclusive. That way we start at a point and end at a point. We don't continue infinitely in both directions. Okay, example. The line segment in 2 space from X naught equals the point 1, negative 3 to the point X1, which is equal to the point 5, 6, can be represented by, and so this is going to equal X equals X naught. It's a line, so it's X equals X naught plus TB. So it's not about the space it's in. When you wonder about how many, in the other equation it was T1 V1 plus T2 V2, right? There's only one coefficient here, so we only put T. It's only one coefficient because we're talking about a line. Okay, that's why it's TV. If we're talking about a plane, it would be T1 V1. It would be X naught plus T1 V1 plus T2 V2. If we were talking about a 3-dimensional object and we wanted to describe it as a vector equation, it'd be x naught plus t1 v1 plus t2 v2 plus t3 v2. So the number of these t's in the linear sum corresponds with the dimension of the space that you're representing using a vector equation or with parametric equations. So since a line is one dimension, you only need one coefficient in this expression. Okay, so this is equal to x naught plus tv, x equals x naught plus tv. So x naught is the point. So it's the line segment from, so our previous equation said that you take x naught plus t, and the vector is going to be the vector x1 minus x naught. And so x naught here is going from x naught, so 1 comma -3 is your initial point, plus t times x1 minus x naught. So this is 5 minus 1, comma 6 minus -3. Okay, and so then this is equal to 1 comma -3 plus t times, and 5 minus 1 is 4, comma 6 minus -3, 6 plus 3, which is 9. So it's that -1 comma -3 plus t times 4 comma 9. Okay, so we now have x is equal to 1 comma -3 plus t times 4 comma 9. And so this is a vector equation representing the line. Okay, and so then okay, so we represent that line. Okay, so recall, you could also do parametric equations to represent it. So recall a linear equation in variables x1, comma x2, comma xn has the form a1 x1 plus a2 x2 plus plus an xn equals b, where a1, a2, meaning each of them, all of them, comma an are not all 0. Okay, so recall that a linear equation in the variables x1, xn has the form where you have this linear sum is equal to a constant, where not all the coefficients, all the a's are, not all of them are 0. And its corresponding homogeneous equation is, well, a homogeneous equation is when you have a linear sum, but instead it equals the constant 0. The word homogeneous, I'm reminding you, is telling you that the constant at the end is 0. That's all it's saying. Okay, and so when you're asked for a homogeneous equation, you want your linear sum to equal specifically the number 0. When you just have a linear equation, it's equal to some constant b. Okay, it's just the added condition that the constant at the end is 0. That's when the added word homogeneous says. So letting a equal to the vector a1, comma a2, comma comma an. So those are the coefficients of the linear expression. A represents, all of them, each of them, and let x be the vector whose components are the unknowns in your equation, x1, comma x2, comma comma xn. So letting that happen, we can express, so this, in the book, this is 15. And in the book, this is 16. So we can express 15 and 16 as a dotted with x is equal to b, and a dotted with x is equal to 0. So we can express 15 and 16 respectively as, I'm just writing respectively because I'm expressing 15 with the first equation and 16 with the second one. The order staying the same. So this whole thing, a1x1 plus a2x2 plus dot 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 plus a and x equals b, where not all the a's are 0, can be expressed as a dot x equals b. But I guess you would also say a dot x equals b and not all the components of a are 0, and a is not equal to 0. Okay. You know what? Let me add that. Okay. So 15 could be expressed as a dot x equals b, where a does not equal 0. And the other one would be a dot x equals 0, still where a does not equal 0. So why is it before I'm saying all the a's are not 0, and in this equation I'm just saying a is not 0? Well, here the a and the x are no longer just a constant for a single variable. Here a and x are vectors. They're n tuples, where the components are each consist of each of the a's in them and each of the x's in them. So the condition that not all the a's are 0 is just saying they can't all be 0. A is a vector, has its components a1, a2 to an. Saying a is equal to 0 is saying that all the components are 0. Saying a does not equal 0 does not mean that all the components are non-zero. Most of them could be 0. Saying a is not equal to 0 just means that there is some component that's not 0. It's just saying that not all the it's not true that all the components are 0, meaning there's some non-zero component. So equivalently, saying the vector a is not equal to 0 is equivalent to saying that not all of the a1 to an are 0. Okay? And this expression a1x1 plus a2x2 plus dot 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 plus a and xn is the dot product of the vector a as we defined it here with that vector x as we defined it there. The dot product of this vector and this vector is the entire linear sum on the left-hand side of this equation. Okay, so as we introduce more mathematical notation, we're writing very long expressions with very short ones. Okay, so this dot product notation is simplifying this really long linear expression as just a dot x. Okay, so a dot x means this entire expression because we're taking the corresponding components of this vector, multiplying each one with the corresponding components of this vector, and then adding the products to get its dot product, which is that expression. Okay, so now we have with dot product notation, we have fast ways to write a linear equation and a homogeneous linear equation. So this represents a linear equation, and this represents a homogeneous linear equation. Okay, let's keep going. So we have that. So next is theorem 3.4.3. And so it says if capital A is an m by n matrix, then the solution set of the homogeneous linear system ax equals 0 consists of all vectors in n space that are orthogonal to every row vector of A. Okay, so if A is an m by n matrix, then the solution set of the homogeneous linear system ax equals 0 consists of all vectors in n space that are orthogonal to every row vector in A. So, okay, so question, what does this theorem mean? Right? What is this theorem saying? Right? So the answer, let's say you have ax equals 0. Right? This is called a homogeneous. Right? Remember how we can express a linear system by a matrix equation of this form, right? So this is called, it expresses a homogeneous linear system because the 0 here is not a number 0, it's a matrix 0. A is a matrix, x is a vector consisting of the unknowns of your linear system. So ax is a product of matrices, which is a matrix. And saying a matrix equals 0 is really saying it's equal to the 0 vector of the same size as the matrix ax. So this is a matrix equation. both the left and right-hand sides are matrices. Everything in this equation is a matrix. Not only is A is a matrix, X is a matrix, and 0 is also a matrix. Okay, so we have a homogeneous linear system represented by this matrix equation. And the theorem is saying that the solution set, the space of all possible matrices X that you could plug into that matrix equation, that space consists of all vectors in n space that are orthogonal to every row vector of A. Well, let's take an example. If you were to take the example, let's say a 3 by 3 matrix, where you said this 3 by 3 matrix times your 3 by 1 matrix X is equal to the 0 3 by 1 matrix. 0 3 by 1 matrix, which is just getting the size of the matrices first. So the 0 matrix is this, right? Here, X is the unknown X1 in the first component, the unknown X2 in the second component, and the unknown X3 in the third component. So let's say you were given a matrix X. You're giving a homogeneous linear system whose coefficient matrix A looked like this. Okay, so let's say we have this weird coefficient matrix here. Okay, so it's saying that all the possible vectors, 3 tuples that you can plug in here, x1, x2, x3, is the space of all vectors that are orthogonal to each row, each and every row of matrix A. Well, that has to be because if you took the first row of A, right, and you took its dot product with this matrix, you would have 1 times x1 plus 0 times x2 plus -1 times x3. But this equation is saying that the dot product of the first row and this matrix and this vertical column matrix, the dot product of those two has to be 0 because the corresponding entry in the first component is 0. This equation is also saying you take the dot product of the second row in this matrix, you get 0 also. It's also saying you take the dot product of the third row in this matrix, you get 0 also. So this matrix equation is telling you that if you were to plug in a vector here, and it satisfy this equation, that all the vectors that satisfy this equation would be the vectors that if you took the dot product of it with the first row, you get 0. If you dot product with the second row, you get 0. And if you dot product with the third one, you get 0. So the space of all vectors that are orthogonal to each and every row of matrix A is the same as the space of all vectors that you could plug into this matrix equation for X, and that it would satisfy that equation. Remember, 2 vectors being orthogonal means their dot product is 0. Okay, so remember that 2 vectors being orthogonal means that their dot product is 0. Okay, so the problem is saying, so the theorem is saying that that the space of all vectors X that can be plugged into the matrix equation AX equals 0 and satisfy that equation equals the space of all vectors X that are orthogonal to each row vector of A. Okay. Okay, so the theorem is saying that that the space of all vectors, they're equal. Okay, so that's theorem 3.4.3. Okay, now new thoughts. Okay, so now I'm not explaining the theorem anymore. So now AX equals 0 and AX equals B are called corresponding linear systems. Okay, so I remember being confused by something like this. AX equals 0 is a matrix equation, but you're calling it a linear system. To me, I found that strange. But in math, when you're representing something by something, you just say it is the thing it's representing. Technically, this is a matrix equation. It's not a linear system. But when you start talking about things, you would just say the matrix equation that represents the linear system is a linear system. Okay, so this matrix equation is called a corresponding linear system to that matrix equation, because what's really happening is that the linear system that this matrix equation represents is corresponding to this linear system that this matrix equation represents. Okay, so mathematicians use shorthand a lot to speed up the conversation. Okay, so this is theorem 3.4.4. The general solution of a consistent linear system AX equals B can be obtained by adding any specific solution of it can be obtained by adding any specific solution of AX equals B to the general solution of AX equals 0. So theorem 3.4.4, the general solution of a consistent linear system, remember consistent means it has at least one solution. So the general solution of a linear system with at least one solution, represented by AX equals B, can be obtained by adding any specific solution of AX equals B to the general solution of AX equals 0. Okay? So this theorem is saying that if you want the general solution of AX equals B, meaning you want to find a representation for all the solutions of AX equals B, all the vectors X you could plug into that matrix equation, AX equals B. I'm calling X a vector as a matrix vector, okay? So if you want to find all the solutions of AX equals B, you can do that by finding all the solutions of AX equals 0 and then translating them or adding each of them, adding all of them by a single solution of AX equals B. Okay? Okay. So that's the end of 3.4. And next is 3.5, which is on the cross product. Okay, so definition 1. If U is equal to the vector U1, U2, U3, so if U is that vector and V is equal to this vector V1, V2, V3 are vectors in 3 space. So you see they're vectors in 3 space, how I wrote it. Then the cross product U cross V is the vector defined by U cross V is equal to U2 V3 minus U3 V2, comma U3 V1 minus U1 V3, comma U1 V2 minus U2 V1. Okay, so when you first look at this, when you first look at that, you say to yourself, I hate linear algebra, right? So you see that and you're like, I don't want to remember that, right? U cross V is equal to U2 V3 minus U3 V2, comma U3 V1 minus U1 V3, comma U1 V2 minus U2 V1. That's U cross V. It's the operation. But there's actually a much, so it's an or in determinant notation. You have that U cross V is equal to this determinant. So the first component you could say is the determinant of the matrix U2, U3, B2, B3, comma, the second component is determinant of the matrix. It's actually the negative of that determinant. It's the negative of the determinant of the matrix U1, U3, V1, V3. And the third component is the determinant of the matrix U1, U2, V1, V2. Okay, this equation is given indexed by 1 in the book. There is no index for this equation. It's kind of a hint to say, don't think of it like that. Okay, so we're starting to think of it equivalently. You can think of U cross V as this matrix, as this three-tuple determinant of this matrix, comma, the negative determinant of that one, comma, determinant of this one. Now this just looks easier to remember because you see it's U2, U3, V2, V3, U1, U3, V1, V3, U1, U2, V1, V2, right? So at least the indices match up with it's just a letter that changes U and V in the rows. You might now you see that, right? But it's still hard to remember that, right? So the solution is, here's a fast way to get this formula. So I'm going to get this formula by doing something on the whiteboard. So let's get that formula without memorizing it. Okay, let's look at the determinants of the matrix I, J, K in the first row. In the second row, I'm going to put the vector U, which is U1, U2, U3 as its components, first, second, third component of the second row. And in the third row, I'm going to put V1, V2, V3. So what I'm saying is that to remember the cross product of U cross V, just remember to find the determinant of this matrix. The first row are components I, J, K, where I, J, and K are the standard unit vectors of R3. So I is the vector 1, 0, 0, J is the vector 0, 1, 0, K is the vector 0, 0, 1. This second row is going to be the components of your first vector in the cross product. So you want to find U cross V, right? So U cross V is equal to the determinant of that matrix. That's what I want to show. But I'm writing it now because I want to say the second row of the components of U, U1, U2, U3, and the third row of the components of V, V1, V2, V3. Let's find the determinant of this matrix. But let's find it. Let's make things easier for ourselves. Let's find the cofactor expansion along the first row of this matrix. Okay, the determinant of the matrix is equal to the cofactor expansion along any row or column of that matrix. They're all equal to the same thing, and it's equal to the determinant of that matrix. Okay, so the determinant of this matrix is I, which is the first thing in that row, times the determinant of the submatrix determined by that entry, right? So it's I times the determinant of, if you remove the first and third rows, you would be left with U2, U3, V2, V3, right? If you, I'm going to erase this in a minute. If you were to, because we're dealing with this entry, right? So if you delete the row and column that it's in, you're left with that matrix there. See that I took the determinant out. So that's right. That's how I'm getting that determinant. And then remember by the checkerboard pattern, plus, minus, plus, minus, plus, minus, plus, minus, plus. This checkerboard pattern is telling you the signs of the terms in the linear sum to get to the cofactor expansion along a row or column. So we're taking the first row of this matrix. So right, so we have a positive I times the determinant of the submatrix. Now we have a minus sign because of the minus there, minus J times the determinant of the submatrix you get from that entry J. Well, if we're looking at entry J, we want to remove the row that it's in, and we want to remove the column J is in. And if we do that, we're left with the submatrix by the entries left, where we just jump over the things we get rid of. But so we have U1, U3, v1, v3, and the determinant of that. But then there's a plus here. Oh, okay, so I want to erase the orange now. Okay, so now for the next entry, so we plus, because the plus sign, the checkerboard pattern, plus k times the determinant of the submatrix you get when we remove the rows and columns that the entry k is in. So k is in the first row, so you remove the first row. K is in the third column, so you remove the third column. So you're left with that submatrix right there. And so you have u1, u2, v1, v2. Okay, and so then this is equal to, so okay, I don't need the orange anymore because I got that. So now, how do you express this with the same? I is the vector 1, 0, 0. This determinant is really a number, okay? This is a number. When you find the determinant of a matrix, you get a number. This is also a number for the same reasons. The determinant of a matrix, which gives you a number. The determinant of that matrix also gives you a number. These are each numbers. But ironically, the I, J, and K are not numbers, they're vectors. So at first glance, you think, okay, I, J are I, J, and K constants, and this thing is the vector, but the opposite. The determinants are the numbers, and the I, J, and Ks are the vectors. Remember, I, J, and K are standard unit vectors of R3. I is the vector 1, 0, 0. Even though I'm using one symbol, the one symbol is representing a vector, and all these symbols are representing a number. J is that standard unit vector in R3. And remember, each one corresponds. It's not the coordinate axis, they correspond with the coordinate axes. K is 0, 0, 1. The correspondence is that they're the unit vectors in the positive direction in each axis. So I is the unit vector in the positive direction of the x-axis. J is the unit vector in the positive direction of the y-axis. K is the unit vector in the positive direction of the z-axis. You can use each of them to generate each of the axes, x, y, and z axes, respectively. Okay, so I is that vector, J is that one. So if you multiply each of these vectors by those constants, then what you're getting is the vector whose first component is u2, the determinant of u2, u3, v2, v3. See how you would get this as the first component if you multiply that by that, right? You'd multiply 1, 0, 0 by that number, that determinant. The first component would be the determinant, and the second, third would be 0. But now you're subtracting, you're in a sense adding the negative of. So the second component would be negative the determinant of that matrix, u1, u3, v1, v3. And then the third component would just be, well, k times this determinant is k times a number. And so multiplying the first two components, which are 0, by that number gives you 0. And then it's 1 times that determinant in the third component. The other two vectors have 0 third components. So if you add this whole thing up, the third component of the sum becomes just the determinant of u1, u2, v1, v2. And so now this 3 tuple is u cross v. And so I'm going to erase the u cross v equals here because the goal was to show this equals it. So finally, that last step, we have u cross v from our definition. We defined an expression as being u cross v. We attained that expression through this operation. So I just showed us that after defining u cross v is equal to this weird order 3 tuple, I found the determinant of that matrix is equal to that same weird order 3 tuple. And so now, instead of memorizing the strange expression to find u cross v, find the determinant of this matrix, and that is u cross v. Okay, so we just went through the definition of u cross v and showed that the determinant of that other matrix is the same as what I defined u cross v to be. It's an easy way to remember how to remember that expression by not calculating it, instead calculating the other thing. So in example 1, you want to find u cross v. You want to find u cross v, where u is equal to the vector 1, 2, -2, and v is equal to the vector 3, 0, 1. Okay, so we want to find u cross v. So u cross v is equal to, well, remember, we have an expression now from the whiteboard to get U cross V. So U cross V is going to equal the determinant where the first row is I, J, K. The second row is the components of U, which are 1, 2, -2. And the third component are the components, the third row are the components of V, which are 3, 0, 1. So now finding the determinant of that matrix means finding U cross V. So this is equal to I times the determinant of the submatrix. That submatrix is 2, -2, 0, 1, minus, because of the change in signs, right, from the checkerboard pattern, minus J times the determinant of the submatrix, 1, -2, 3, 1, plus K times the determinant of the submatrix, remove the first row, third column, 1, 2, 3, 0. Okay, and so now you just compute that and you get U cross V. So it's I times the constant 2 minus 0, which is 2, minus J times, the parentheses is just the number that I'm just separating from keeping the order the same. 1 minus -6, which is 7. So that determines the 7 plus K times the term. The other one, which is 0 minus 6, which is -6. So this is equal to 2I minus 7J minus 6K. Okay, and you could, that is a representation of U cross V. If you don't like the representation in terms of I, J, and K, you can also see this as 2, -7, -6. Okay, the coefficients just correspond with the components of the vector that the linear sum represents. Is there a question? Okay, so U cross V is equal to that 3 tuple right there. And we use the determinant method to find U cross V. Okay, so next is theorem 3.5.1, which says if U, V, and W are vectors in 3 space, then A, which is U, or A, which is U dot U cross V is equal to 0. Okay, so this is from the fact that U is orthogonal to U cross V. Okay, U is orthogonal to U cross V. So if you okay, let me write. So I'm going to go to the whiteboard to illustrate this. If you have a vector U, right, and you have a vector V, okay, that's a vector U and a vector V. If you were to find U cross V, it would be a vector that would be perpendicular to both U and V, okay? So U cross V is actually perpendicular to both U and V, but actually I drew the directions wrong. I'm just going to fix that. I was thinking of switching U and V. I think it would be better to write it this way. So that's the direction of U cross V. And you're probably wondering, how did I know that it was going down instead of up? And I'm going to explain that to you. That's called the right-hand rule. So, so U cross V is that way, but U cross V is perpendicular to both U and V. But the fact that I wrote the other way is pointing something out. Just because you know that a vector is perpendicular to 2 other non-collinear vectors, it doesn't mean you know the direction of the vector, right? There are actually 2 directions a single vector perpendicular to 2 other ones could take. This one could have gone down left or up right. But U cross V has a specific direction. In this case, it's downward. Okay, and so I'm not going into it yet, but it has something to do with the fact that the direction from U to V is clockwise. Okay, you're going clockwise here to go from vector U to vector V. That clockwiseness of going from U to V is telling that U cross V is going down, not up. Okay, so that's what it has to, that's what's the direction is determined by. Okay, so u dot u cross b is 0. That was the point. We'll go back one more time. So u dot u cross b is 0 because u, the vector u and u cross b are perpendicular to each other. So you see this perpendicular sign here, right? So u dotted with u cross b has to be 0 because they're perpendicular. Okay, so the fact that geometrically they're perpendicular vectors, and so when you take the dot product, it has to be 0. So part A is saying that the dot product of those two things are 0. For part B, if you take the vector v and you dot it with u cross v, it's also equal to 0, but it's for the same reason. V is also orthogonal to u cross v. V is orthogonal to u cross v. Now, from what we've said, it's you couldn't. It's not direct from that, but from my picture, you see that the fact that v, what I'm telling you is that v and u cross v are perpendicular, and that means their dot product has to be 0. Okay, so the fact that the perpendicular, circled in the purple, the perpendicular sign there, they're perpendicular, and that's telling you that the dot product is 0. So A and B are very similar. Okay, C, but u, for u cross v, u is the first vector and v is the second one. So it is saying that it's not exactly the same statement to say that the first vector dotted with the cross product is 0, and saying the second vector dotted with the cross product is 0. Okay, and C, if you take the norm of u cross v, and you square it, it's equal to the norm it's equal to the norm of u squared times the norm of v squared minus u dot v squared. It's called Lagrange's identity, but you don't need to know the name. D, if you have u cross, it's in the book, these names, if you want to know them. U cross v cross w is equal to u dotted with w times v minus u dotted with v w. And E says that u cross v cross w is equal to u dotted with w times v minus v dotted with w times u. Okay. When you look at formulas D and E, u dotted with w is a number. Okay. So different operations can give you different results, right? When you dot two vectors, the result is a number. When you cross two vectors, the result is a vector. So in A and B, u cross v is a vector. But then you take that vector and you're saying u dotted with the vector is 0. And in B, you're saying the vector v dotted with the vector u cross v is 0. You dot product vectors, the result is a number. Okay. So in this equation, we're saying the number u dotted with w times the vector v minus the number u dotted with v times the vector w. So u dotted with w is a coefficient of v. It's a number that it's you're multiplying a vector by a constant there. And here you're also multiplying a vector by a constant. Okay, it doesn't look like a constant, but it is one. Okay, so that's theorem 3.5.1. It applies to three vectors u, v, w in 3 space. Okay, we're being specific about the space we're in. We're considering 3 tuples here, u, v, and w. The next theorem is theorem 3.5.2. If u, v, and w are any vectors in 3 space, and k is any scalar, then, so k is a number, A says u cross v is equal to the negative of v cross u. So remember, I said that it being the first and second component matters, right? For A and B before, I was saying these are slightly different results because u is the first component, u is the first thing and v is the second thing. So u cross v does not equal v cross u. U cross v equals the negative of v cross u. Okay, so it's not commutative, it's the name for it. So it matters which vector is first and which vector is second when you cross product. Okay, it's against your intuition. You're used to saying 2 times 3 is 6, and when you do 3 times 2, you get the same number, right? So you've been taught to see multiplication, to see when you see a multiplication symbol, thinking of multiplying two things where the order doesn't matter. So you have to unteach yourself that. Multiplication that's still true, but we're not multiplying. This is the cross product. We're using the same symbol to represent a different operation. Okay, so this cross product operation is not commutative. And so u cross v equals the negative of v cross u. B, u cross v plus w is equal to u cross v plus u cross w. So this multiplication has the same property. And so this is easy to believe and it works. It's good that most of the rules of multiplication match up well with this. But the confusion that this causes is that there are some things that are different, like A. A is different, right? U cross v equals the negative of v cross u. And so most of the properties are the same, but some are different. And so you have to keep in mind which are the same, which are different. Okay. So you have u. Oh, I was muted. Okay. I'm back. I don't know when you stopped seeing me or hearing me. Thank you. Okay. Did you hear all I said about theorem 3.5.1? Or was I in the middle of explaining it just a second ago? Okay, that's great. Okay, so you heard me talk about A and B. Okay, so for C, u plus v cross w is equal to u cross w plus v cross w. Okay, so that's the same as your intuition would tell you. K as a constant times the vector u cross v is equal to ku cross v. And it's also equal to u cross kv. Okay, so what this is saying is you can move around this constant sign. Instead of k times u cross v, you could say ku cross v, or you could say u cross kv. So you can move the constant around, and it doesn't change the value of the expression. E says that u cross 0 is equal to 0 cross u, which equals 0. Okay, so this is another example of how the 0 sign means different things, and it depends on context, right? So when you're looking at a symbol like 0, context matters. It's all about context. This context is telling you, well, the operation is a cross product. The cross product is an operation on two vectors, right? The result is a vector, but also you can only take cross products of two vectors. You can't take a cross product of a vector and a constant. And so you have to assume, you're assuming that you're assuming as a reader that when you read something in math that it's right. And so when you're reading u cross 0, what that means is that 0 is a vector, okay? And so 0 sum here is representing a vector, and it's representing a vector the same size as the vector u, okay? So there's 0 vectors for each size of a vector, right? There's a 1 component vector 0, which is just 0, basically. There's a 2 component vector 0, which is 0, 0. There's a 3 component vector 0 vector, which is 0, 0, 0. They're all 0 vectors. There are infinitely many 0 vectors. But you know which you not only know, just from writing the number 0 there, you not only know it's a vector, you know the number of components of that 0 vector. It's the same as the number of components of u, because when you cross product two vectors, when you cross product two things, they're both vectors and they're both the same size. So u tells you that you're dealing with vectors and that you're talking about vectors of a certain fixed size. Okay, so u cross var is a product of two vectors, and that's just saying that you could say u cross 0 equals 0 cross u, and it equals to 0, where again 0 is a vector, and 0 is the same size as the vector u. So if you take if u is a two-tuple, a vector with two components, then u cross 0 is the two-tuple u cross product with the size 2 0 vector 0, 0 is equal to 0, 0 cross u, and that's equal to the two-tuple 0, 0. Okay, so the size of u is telling you what 0 is throughout. Okay, this 0 is also a two-tuple. That's a two-tuple, and this is a two-tuple. Okay, if the operations got weirder, then this 0 could be something else, depending. But the operations, or every operation here, is telling you that this is a two-tuple. Okay, if we had a chain of 10 equal signs, at the end of it was equals 0, it's possible that that 0 at the end might be different than the original 0 at the beginning. Okay, but it's still the same sign. That's E, and then F is saying that when you take u cross with itself, u cross u equals 0. So when you take a vector and you cross product with itself, it equals 0. The vectors u does not have to be the 0 vector. It can be any vector. So for any vector, even all the non-zero vectors, which are most of them, almost all of them, you take cross product with itself, and it is 0. Okay, so these are all A through F are additional statements about the cross product. 6 additional statements in Theorem 3.5.2. These are for vectors u, v, and w in free space, where k is a scalar. Okay, as a note, if you take the so for the below equations, I, j, and k are the standard unit vectors of R3 of 3 space. Okay, so I is 1, 0, 0, j is 0, 0, 0, 1, 0, and k is 0, 0, 1. So I, j, and k are the standard unit vectors of R3. So if you take I cross I, it has to equal 0, because property F tells you that when you take a vector and you cross product with itself, you get 0. If you take I cross j, well, then that's equal to k. You can do the calculations, and you would get it equals k. This is from, so I'm going to put side work here. If you were to take, if you take I cross j, what that's equal to is the 1, 0, 0 vector cross with the 0, 1, 0 vector. And we know it's the determinant of the matrix. So this is a little bit weird because we're using I, J, and K in it when we're talking about the cross product of I, J, and K. So this is 1, 0, 0. The I, J, K at the top has nothing to do with the I cross J that we're cross producting. This is 0, 1, 0. And so when you take this cross product, you get I times the determinant of the submatrix. Copy that. That's 0, 0, excuse me, 1, 0 minus j times the submatrix 1, 0, 0, 0 plus k times the submatrix 1, 0, 0, 1. And so now this is equal to I times, well, the determinant of that matrix is 0, minus j times the determinant of that matrix, which is also 0. And then plus k times the determinant of that matrix, which is 1. This equals k. 1 times k is k. So I just showed that I cross j is equal to k. That's the second equation there. Okay, so just by calculating cross products, when you do I cross j, you'll get k. And then you can do the same thing for the other for these other ones I'm going to write down. So j cross I is equal to negative k. Um, j cross j is equal to 0. Same reason. If you take k cross k, it equals 0. Already showed this one. I cross j is equal to k. J cross k is equal to I, and k cross I is equal to j. J cross I is equal to negative k. K cross j is equal to negative I, and I cross k is equal to negative j. Okay, so we have 9 equations. So we have 9 equations taking cross products of 2 of the 3 standard unit vectors of R3. Okay, so just like when we took the determinant, we got a simple way to talk about u cross v, even though it's complicated. There's a simple way to remember these 9 equations. Okay, so I'm going to illustrate that on the whiteboard. Okay, so the point what I'm going to do now is to show a quick way to remember all 9 of these equations. Okay, well, before I go to the whiteboard, actually, let's look at the first row, right? So we know that the cross product of a vector with itself is 0. So I cross I is 0, j cross j is 0, and k cross k is 0, from the property that u cross u is 0 for every vector u, free space, right? So all 3 of these equations is just from that. So you know that without having to remember anything. If you know this property, remember it, then you know these 3 equations as a byproduct of that. Now these next equations are next, right? Now let me note that if you knew that I cross j equals k, then remember the part A of theorem 3.502. It says u cross v is equal to negative of v cross u. So if you switch the order of the vectors that you're cross producting, the result is the negative of what you originally had. So if you know that I cross j equals k, then j cross I is the negative of the other one. Well, since I cross j equals k, then j cross I would have to be negative k. So knowing this equation, you then know that one from the other property. If you know that j cross k is I, then k cross j is just the negative of that one, which is negative I. And if k cross I is j, then flipping it as I cross j gives you the negative of that, which is negative j. Okay, so before I went to the whiteboard, these 3 equations are from the fact that a vector cross product itself is 0, and these 3 are just deduced directly from those 3 correspondingly, right? So remembering these 9 equations essentially is coming down to remembering those 3. Okay, if you remember those 3 equations, then the first 3 are easy, and the other 3 are just derived directly from those 3 by switching the vectors that you're cross producting, and then the result is the negative of what the original one was. Okay, so the memory technique I'm going to tell you about is just remembering those 3. Okay, and then you remember the 2 properties and you get the other 6. Okay, so if you draw a circle and you have, let's say, I here, j here, and k here. And notice that the order, right, the order goes by like I, j, and k, the alphabet I, j, k. And when you think of normally when you think of a circle and you want to give an orientation, a direction, your first natural instinct might be to give it a clockwise one, right? Because whenever you're looking at something, whenever you think of the direction of something along a circle, you look at clocks. You've looked at clocks hopefully before, right? Before computers were around, people would use clocks and they would read it often, right? And so you would go clockwise like this, right? So so the I, j, and k are in the direction, clockwise direction. So if you're going clockwise, right, you would see I, then j, then k, and then k would go back to I, right? This is clockwise. Okay, so that's the clockwise direction. So then if you just draw this picture, or maybe visualize your head correctly, then you do, if you were to do I cross J, the result is just the next vector going in the clockwise direction in this picture. Remember, this picture is not telling you the reason for anything. It's just to remember things. So I'm not justifying that I cross J equals K by drawing a circle and having arrows point, right? So I'm not justifying the statement. I'm just helping remember it. So I cross J equals K, because in this picture is reminding you of that, because the order clockwise is I, then J, and then K. So I cross J is K. And now if you take a J cross K, I'm not going to tell you the answer. Just think to yourself, what is this picture following that idea? What would this picture possibly be telling you what J cross K is? Right? It's telling you equals I, right? Because I is the next thing clockwise. J, then K, and then K goes to I in this picture. So J cross K is I. And then if you do K cross I, then that equals K cross I, and then the next thing is J. So this picture is showing you that K cross I is equal to J. And so these are the three equations that were left to understand how to remember from that note I wrote down. I cross J is K, J cross K is I, and K cross I is J. Okay, so by drawing a circle and IJK in the clockwise direction, you get those three equations. All right. So now it's a quick way to remember those three. The first, so you have a quick way to remember those three. These three are derived directly from those three, and then the first three are just a vector cross product with itself 0. So you might say, well, how do I know that? How do I remember that J cross I is negative K? If I needed J cross I is negative K, and that helps you remember only those other three, just take a step backwards, right? If you have J cross I is negative, if you want to know what J cross I is, just take a step backwards and think of I cross J, what that is, and then J cross I is the negative of that. Okay. Though I guess you could. I don't know if this is the best way to remember it now, but okay. So this is. Then it requires you to remember two things. I sometimes like to reduce things because I have to remember a lot of things. So I wouldn't want to remember it this way, but maybe you do, right? So you could use this picture to remember the other three also. And this is how you would do it. So if you were to do, if you wanted J cross I, okay, and you wanted J cross I, but without finding I cross J first, just directly from the picture, then think, well, you're assigning the direction clockwise, right? So if you were to go in the counterclockwise direction, that would be, let's say, the negative direction, right? So if you were going to go in the counterclockwise direction, so if you were going in the counterclockwise direction, that would equal the negative direction, right? Because we're in a sense starting with the clockwise direction. So if you go along the circle in the negative direction, the counterclockwise direction, and you want a J cross I, well, you'd start at J and you'd go in the negative direction to I. And you know it's negative because you're going counterclockwise. You draw the I, J, and K the same, and it's clockwise. So you're going negative direction. That means the result, the next thing is K, right? Because if you're going counterclockwise, you have J and I. Next would be K. But because you're going the negative direction, this memory technique is telling you take the negative of the next thing you see. So J cross I is negative K. Now, if you keep going in negative direction, you would go I to K. So then if you take I cross K, that would equal, well, if you kept going, the next thing would be J, but because you're going in the negative direction, that equals negative J. And then if you kept going in counterclockwise direction, you have K cross J. And K cross J, first K, then J, after that would be I, but if you're going in the negative direction, K cross J is equal to negative I. And so you could get all 6 of these equations with just that one picture if you add a little bit more of memorization technique to the same picture, right? But the added thing now is that you have 2 directions. Clockwise direction is the positive direction, and the counterclockwise direction is the negative direction. So that might be easier. But even if you forgot this other second thing, you could find any of the first 3, take as negation, get the other 3. Okay, so clockwise direction, which is the positive direction, which equals the positive direction. Okay, before we weren't dealing with the positive direction because we weren't talking about a negative direction. If there were no opposite directions, then there would only be one direction. Now we've added a second direction, so now we have positive. Okay, so we have positive direction and negative direction. Okay, so now we have all 9 equations there. Okay, so keep going. So an example. So the example is if the vector u is equal to the vector 1, 2, -2, and the vector v is equal to 3, 0, 1. Then u cross v is equal to, okay, well, you just take the cross product of those 2 vectors. I don't want to do this now. Do it. I, j, k. So we already did examples of this. 1, 2, -2, 3, 0, 1. And so this is I times the determinant. What do I do? I still have that. Good. I 2, -2. Did I already compute this? 1, 2, -2. 3, 0, 1. Okay, I already computed it. We don't need to do it again. Okay, so I just, it's the same example I just did. It's right here. Okay. 2, -7, -6. Yep. Okay, good. Same example. Let's keep going. Okay, so the next thing is, the next question is, how do you know the direction of u cross v given the direction of vectors, given the directions, they have each of their own directions, given the directions of vectors u and v. Okay, so how do you know the direction of u cross v given each of the directions of vectors u and v? Yeah, just pointing out there's 2 directions there. Okay, so the answer is the right-hand rule called. Okay, so the right-hand rule tells you the direction of u cross v given the directions of u and v. Okay, so for that, I'm going to draw a picture. So, okay, good. Okay, so let's say you have a vector u. And you have a vector v. And you have an angle theta between them. And then you want to say, well, what is the direction of u cross v? We can calculate the magnitude of u cross v. Well, you can find u cross v, right? You can find the vector u cross v using the formula, right? And technically that would give you the direction. But you could take the magnitude of it and you could find its length. But just drawing a picture of u cross v. Actually, I'll go into the magnitude also, but okay. So, okay, so here's u cross v. It's in this direction with certain magnitude. It's the right-hand rule is how you find this direction. Okay, so this is an illustration of the right-hand rule used to find the direction and only the direction of u cross v. Okay, so the right-hand rule only gives you the direction of u cross v. It does not tell you the magnitude of it. Okay, so this is an illustration of the right-hand rule used to find the direction and only the direction of u cross v. Okay. So I'm going to draw a picture of a hand. So let's see here. Thumb. Got this going up here. Got this. 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 It's got kind of chubby hands. Now we have. Wait. No, 4. There. 2, 3, 4. Okay, so actually, fix my picture. Okay, but then. Okay, so then. All right, let's speed this up. Okay, so then. And so then here's the nail. This person's nails. Nail over here also. Okay, so this is the person's hand. Okay, it's the person's right hand, right? If you're holding your right hand, right, and then you're facing it like this, you see how the thumb, I'm trying to be very specific with the picture about even where the thumb is, right? So it's not a coincidence that the thumb is where it is. Now in the screen, there's like a mirror image. So when I put my hand up on the screen, it's looking kind of opposite. You should go by the picture. So the thumb, your thumb is pointed upward, and when you curl your fingers, the picture is important about how you draw the hand. So the details of the picture matter, okay? So the thumb is pointed upwards. You don't have to draw a picture of a hand to do this. You just need your hand. But me teaching it to you, the details of the picture matter. So the thumb is pointed upwards, right? The thumb is telling you the direction of u cross v. Okay, so the thumb is telling you the direction of u cross v. The direction of your thumb is the direction of u cross v. Okay, now if you do the right hand rule wrong, then the direction of your thumb is not the direction of u cross v. I should point that out. Just because it could confuse you. If you're doing the right hand rule wrong and your thumb is pointing a certain direction, it doesn't mean you change the direction of u cross v. You willed it by moving your thumb in a different direction, right? So you have to do the right hand rule correctly, and then the direction of the thumb is the direction of u cross v. Because so that statement is really is implicitly saying that you're following the right hand rule correctly. Okay, so the direction of your thumb is the direction of u cross v. So now imagine the axis, the vector u cross v. Imagine curling your fingers around the axis, not by looking at me, but by looking at the picture. So I think the picture you're looking, it's as if I'm looking at a mirror. So you should go by the picture. So that you have the thumb pointed in the direction u cross v, and your fingers are curled around the vector u cross v. I'm explaining in the opposite direction. I'm starting with the answer, and I'm going backwards to the given to show you how this is explained. Okay, so u cross v is in the direct. I know I need a few more minutes. So the thumb is going in the direction of u cross v, and your fingers are curling around the vector. Notice that this is hard for people to see. Your fingers in the picture, not on the screen, but the fingers in the picture. Notice if after they're curled, right? If you were to go backwards in time to before I curled them, if you were to open your fingers up a bit, do you see that the fingers would be pointing from the vector u to the vector v? That the fingers are in a sense curled in the direction of theta, going from vector u to vector v? That's what you want. The first step is to get your fingers to go in the direction of from vector u to vector v. And if your fingers are curling in the direction from vector u to vector v, then the direction your thumb is also in is the direction of u cross v. Okay, you're not allowed to dislocate your thumb or remove your thumb and put it somewhere else if this isn't working, right? If your fingers are going from vector u to vector v, and you don't like where your thumb is pointing, you can't move your thumb somewhere else in your hand and say, okay, now it works, right? The direction of your thumb is actually the direction of u cross v if you're curling your fingers correctly. Okay, if you already know the direction of u cross v and you're looking at your fingers and you're saying it's curling from U to V, but the thumb is in the wrong direction, it's the opposite. Your fingers are then not being curled in the direction from vectors U to V. Okay, so the direction you need, step one is to get the direction of your fingers from U to V. And then step two is your thumb is directed in the vector. Your thumb is in the direction of U cross V. So on the next slide, I'm going to write those steps so I don't screw up the picture. Okay, so step one is curl your fingers in the direction. Oh, I should say this. Step one is have your fingers spread out, so that they are pointing towards vector U. Okay, so your fingers, you can have your fingers out and just in the direction of vector U. Maybe it's a mirror, maybe it should be that way, right? Wherever U is, your fingers are just pointed in that direction. Okay, so you imagine the starting point of the vector here, and then it keeps going, or here, your fingers are just pointed in the direction of U. So step one's easy. I think like most things in life, the middle step is the hardest part. So step two, the middle is the hardest part usually. So step two is that curl your fingers so that they curl in the direction from vector U to vector V. Okay, so keep in mind that you may need to rotate your hand to modify where it was at the end of step two, at the end of step one. Okay, so step one, you have your fingers pointed in the direction of U, and then you want to curl your fingers in the direction from U to V. You may get lucky and your fingers are pointed in the direction of U, and that when you curl your fingers, you're going in a direction from U to V, and it works, and your thumb is in the right direction. Or you may get unlucky and you point your fingers in the direction of U, but then when you start curling your fingers, they're not going from U to V. That's okay. All you have to do is turn your hand 180 degrees, flip it. Wait, no, not flip it. Well, yeah, 180 degrees, but not in this direction. So that your fingers are still pointed in the same direction, but your palm, inside and outside your hand, are now opposites. And then your fingers are still pointed that way, but your thumb is now in the opposite direction from what it was. Then when you curl your fingers, you're now curling in the opposite direction. And so the opposite direction will be going from vector U to vector V. One of those directions is going from U to V, either this way or the opposite way. Okay, there's only two directions you can go from vector U to vector V. You either go this way or the opposite way. So one of those two. So then after step two, you're not only are your fingers originally pointed in the direction of vector U, but when you curl your fingers, they're curling in the direction from U to V. Step three is keep your hand in the exact same position as it was in step two. Okay, so another mistake people make is that they move their hands when they're done with step two and start thinking about step three. Keep your hand exactly where it was in step two. So keep your hand in the exact same correct position as it was in step two. The direction of your thumb is the direction of the vector U cross V. And now you're done. So those are the three steps to the right hand rule. Okay, so I'm going to save this slide. I'm going to click save now because the lesson's done in a few minutes and I'm not going to write anything else. So this will be on Blackboard, so you can look at these whiteboard slides. Okay, so step one, fingers in the direction of U. Step two, fingers have to curl in the direction of from U to V. Step two may require you to move your hand, in a sense, go backward to step one, and your fingers will still point in the direction of U, but you may have to flip your hand, rotate it so that it's still in the direction, your fingers are still in the direction of U, but when you curl them, it goes from U to V. Once you have your fingers curling from in the direction of U to V, then the direction of your thumb, without moving your hands at all, your direction of your thumb is the direction of U cross V. Okay? Those are the 3 steps for the right-hand rule. You have to practice it in order to get it right. Okay? Once you get it, yeah, okay, the lesson's going to be very soon. Okay, so then once you get it, you know it's right. If you're uncertain, there's a chance it might be wrong. Okay, so before you go, let's just quickly talk about what the homework is going to be. So, okay, so we finished 3.4 and we're on 3.5. So the homework is for 3.4. Okay, so exercise set 3.4, numbers 11 and 19 are the homework. Okay, not there. Okay, so the homework for next class is exercises from 3.4. Okay, and so the 3.4 from the sheet, numbers 11 and 19. Okay, 3.4 numbers 11 and 19. Okay, exercises 3.4 numbers 11 and 19. So that's the homework for next class. Okay, you got all of your exams. I emailed them to you earlier today, so you'll have them. If you have any questions, you can ask me about it here or tomorrow during office hour. Have a good night, and I'll see you all next class. Okay, bye. Good night. Thanks for being here. Good night. See you later.